Hey guys, this is going to be my first attempt at using the emulator software. Thank you very much, Nathan. Let's see if it works. So before we start, we have to talk about a few pieces of vocabulary. The first thing is a limit. So let's take a look real quick at the function x squared. Okay? When you look at x squared, you can see that it goes up. I have to plug in my computer. We would say that the limit as x approaches infinity equals infinity, and the limit as x approaches negative infinity equals infinity for the function y equals x squared. Let's look. As x approaches infinity, that means as x gets really, really, really big, y gets really big. Now it's hard to see it because we're only looking at a 10 by 10 window, but if we change the window and we make the y max go up to 1,000 and we make the x max go up to 100, watch what happens. See how the graph keeps going up? It'll keep doing that all the way to infinity. Same thing to the left if we make the x min negative 100. The graph keeps going up. So as x approaches negative infinity, as x moves this way, y continues to go up to infinity. And as x approaches positive infinity, y continues to go up to positive infinity. So that's what a limit means. A limit is something that you get closer and closer and closer to, but might not ever actually hit. And that's actually the definition of an asymptote. An asymptote is a line, a graph approaches but never touches. And that's kind of a broad statement because sometimes the graph will cross the asymptote, but we're talking on the ends of the graph, and I'll show you one in a minute where it crosses over that value, but you can tell that on the ends, as x approaches positive and negative infinity, the graph is asymptotic to that line. So it's easier to just talk about certain graphs and certain examples. So let's do that. Let's talk about the function f of x equals 2x squared over 4 minus x squared. We're going to talk about horizontal and vertical asymptotes. Now it's important to, how do I make this thing go away? Go. It's important to understand that this is vertical and this is horizontal. So a vertical line has an equation of x equals a number. Even though the y, let's back up. Let's talk about that. Everybody has trouble remembering the equation of a horizontal and a vertical line. So let's talk about a graph. If we talk about this line, let me change colors. If we talk about this line, what are all the x values on this line? Well, think about these coordinates. This is 1, 1, 1, 2, 1, 3. Notice how the x values for all of these points is, 2. Jeez, I'm not on my game today. The x value for all of these points is 2. The vertical line is called the line x equals 2. Whereas a horizontal line, like this, wow, I'm off today. Say that's 1, 2, 3. All these coordinates are going to have a y value of negative 3. Think about this would be negative 1, negative 3. And this would be negative 2, negative 3. A horizontal line is a line y equals a number. In this case, y equals negative 3. So when we talk about vertical when we talk about vertical asymptotes, the equation of the lines are going to be x equals a number. And when we talk about horizontal asymptotes, the equations are going to be y equals a number. Let me pause and plug my computer. Okay, now we should be good to go. So, horizontal, y equals a number. Vertical, x equals a number. Now, we define a horizontal asymptote. The formal definition is kind of mathy and gross, but I'm going to give you some cheats to remember it. But the definition of a horizontal asymptote is the line y equals b such that how do I explain this? Let's just look. It's too hard to write the mathy terms that you'll understand because there's so much going on. Okay, horizontal asymptotes. Those are the harder ones, so we're going to get those out of the way first. There are 3 rules for horizontal asymptotes. Asymptotes. We're going to call m the power of the numerator. The highest exponent in the numerator. We're going to call n the power of the denominator. The highest exponent in the denominator. So here's your 3 rules. 1. If m is greater than n, there is no horizontal asymptote, meaning there's no horizontal line that, as the limit as x approaches it, will be infinity. The limit as x approaches infinity will not be equal to it. Okay. Step 2. If m is less than n, the horizontal asymptote is y equals 0. Now hopefully you know that y equals 0 is the x-axis. That will be the horizontal asymptote if the numerator exponent is less than the denominator exponent. Finally, if m equals n, if the powers are the same in the top and the bottom, the horizontal asymptote equals coefficient over coefficient. Now, like I said, I'm going to do a lot of examples, so I won't leave you high and dry here. But let's look at this example first. Notice how the exponents are the same. The highest exponents in the top and the bottom are 2. That means we're going to look at step 3. The coefficient of the top is 2. The coefficient of the bottom is -1. That means the line y equals -2 will be a horizontal asymptote. Now let's look at the graph. On is helpful. Y equals 2x squared divided by, actually I have to put that in parentheses because it's a power. Divided by 4 minus, oops, I gotta put that in parentheses too. Man, I am off tonight. X squared. This is the same function we just talked about. Let's look at the graph. Alright, I'm in a nasty window right now. So remember, to get back to your 10 by 10, you just do zoom 6. Notice, when y equals -2, that's this line right here, the graph as x approaches -infinity equals -2, and the graph as x approaches positive infinity equals -2. That's a horizontal asymptote. Now let's talk about the vertical asymptotes. A vertical asymptote occurs, we're talking about f of x equals 2x squared over 4 minus x squared. You only have vertical asymptotes. Only have vertical asymptotes in rational is that it? Rational functions? Yes, rational functions. I can't think of another function that has a vertical asymptote other than a rational function. So a rational function, that means a fraction. Vertical asymptotes only occur when you have a fraction. And the way you find a vertical asymptote is to set the denominator equal to 0. So 4 minus x squared equals 0. Solve, so I'm going to subtract 4 from both sides. Divide by -1. And take the square root. Those are my two vertical asymptotes. Go back and look at the graph again. See how the line x equals -2? The graph approaches it but never touches it. And the line x equals +2. The graph approaches it but never touches it. Those are called vertical asymptotes. Your graph might have a dotted line there. There's a way to turn those on and off. I'm not going to get into it right now. But just know, it might even be a solid line. Some of them have a solid line. But know that if you have a straight up and down line, that's an asymptote. And you should always know, based on the function itself, what the asymptotes are. So the next example I'm going to do is to identify the asymptotes of this graph. F of x equals x over x squared minus x minus 2. First thing we're going to find are the vertical asymptotes. So we're going to set the denominator equal to 0. And this is an easy one to factor. So we go x minus 2, x plus 1. Draw your t. X equals 2. X equals -1. When we look at this graph, it should have a vertical asymptote at 2 and a vertical asymptote at -1. Let's talk about the horizontal asymptotes. Because the denominator is bigger than the numerator, y equals 0 is going to be a horizontal asymptote. That means the limit as x approaches positive infinity, as we go all the way to the right, it's going to equal 0, which means the graph is going to get really, really, really close to 0, but never actually touch 0. And the limit as x approaches negative infinity is also going to equal 0. So let's look at this graph. We should have a vertical asymptote at 2 and -1, and a horizontal asymptote at y equals 0. So we have x divided by the quantity x squared minus x minus 2. Oh, jeez. There it is. Now, this one is called, somebody at this conference just talked about a conditional asymptote, because the definition of asymptote is a line the graph approaches but never touches, but you can see that it goes through 0 right here. So what we're talking about is on the ends of the graph. As x approaches positive infinity, and again, let's zoom in. Let's make our x maximum 1,000. So we're looking at the right-hand side of the graph. Notice how the graph is really hard to see. That's because it's getting really, really close to 0. I'm going to do something I learned today, and I'm going to make the graph thicker. So I arrow over to that line, and I just skipped it. Awesome. So now my graph should be thicker, and hopefully we'll be able to see it. See, there it goes. It's getting really, really, really close to 0. But it's never actually going to equal 0. Now let's go back to the regular 10 by 10 window and notice the vertical asymptote at x equals 2, that's right here, and the horizontal asymptote at x equals -1, that's right here. There's a couple examples of asymptotes. Now, an asymptote, an example of a function where there isn't a horizontal asymptote, but there is a vertical asymptote, would be something like well, wait a minute. Yeah, no horizontal but vertical. Got it. So I need the numerator to be greater than the denominator. So let's look at a function like x squared plus 4 over x minus 2. That's going to have a vertical asymptote at x equals 2, but because the numerator is bigger than the denominator, there should be no horizontal asymptote. So in the numerator, we're going to go x squared plus 4 divided by x minus 2. Now there's more of the graph up there. There is a vertical asymptote at x equals 2, and there's what we call a slant asymptote. And I'm going to talk about that in a minute too. But let's go up here. So I want to see this part of the graph, which means I'm going to increase my y max so I can see more up here. So instead of y max being 10, I'm going to make it 100. Now you can see the vertical asymptote at x equals 2. Okay, so that's how you find horizontal and vertical asymptotes. Now I also want to talk about this idea of end behavior. In order for us to do that, you need to know what the graphs of y equals x, y equals negative x, y equals x squared, y equals negative x squared, y equals x cubed, y equals negative x cubed, and then all the odd and evens from here are pretty similar. Y equals x to the 4th and y equals negative x to the 4th. Now you guys kind of mentioned something like you'd heard last year about up, 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 down, and all that. Hopefully you know that y equals x looks like this, y equals negative x looks like this, y equals x squared looks like this, y equals negative x squared looks like this, y equals x cubed, y equals negative x cubed, and then x to the 4th and negative x to the 4th. Those are just basic shapes of these 2, 4, 6, 8 functions. But what you need to understand is the end behavior of these functions. Notice that for this one, as x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches negative infinity. For negative x, it's exactly the opposite. As x approaches infinity, y approaches negative infinity. And as x approaches negative infinity, y approaches infinity. For y equals x squared, they're both positive infinity. For negative x squared, they're both negative infinity. For x cubed, as x gets really, really big, y gets really, really big. But as x gets really, really small, y gets really, really small. For negative x cubed, it's exactly the opposite. As x gets big, y gets small. As x gets small, y gets big. For x to the 4th, it's the same as x squared. Up, up. Negative x to the 4th, down, down. So that comes in handy when we're analyzing functions such as y equals 3x over x squared minus 2. Notice the bottom is bigger, so the horizontal asymptote is y equals 0. That one's easy. 3x squared over x squared minus 2. The exponents are the same, so y equals 3 would be the horizontal asymptote. For the function y equals 3x cubed over x squared minus 2, in this case, there is no horizontal asymptote. So back up, hold on, back up. For this one, the limit as x approaches infinity is 0, and the limit as x approaches negative infinity is 0. For this one, the limit as x approaches infinity is 3, and the limit as x approaches negative infinity is also 3, because it's coefficient over coefficient. For this one, there is no horizontal asymptote, so that's when we have to talk about end behavior. And the way you find end behavior is to divide by the greatest exponent in the denominator. So let's talk about that one. It was 3x cubed over x squared. It was 3x cubed over x squared. I think it was minus 2. So we know there's no horizontal asymptote, but the end behavior, so we divide by the x squared. So we're going to do 3x cubed over x squared. Now there's going to be some big remainder and stuff, but basically what happens is you end up with 3x. And that's just a variation of the line y equals x. So the end behavior of this function is going to act exactly like the line y equals x. As x goes to infinity, y is going to go to infinity, and as x goes to negative infinity, y is going to go to negative infinity. Let me show you that on the graph. So the function is three x cubed, cubed, and then I have to push this button. I got a new operating system, so I got to get used to it. Divided by x squared minus 2. Now it's going to be a really funky looking graph. Oh, hold on, I'm not at Zoom 6. Zoom 6. It's pretty funky looking. Why isn't that all that funky looking? 3x cubed over x squared minus 2. But we don't care really about what it looks right here. All we can tell by this picture is that it doesn't really have a vertical asymptote. It does have a horizontal asymptote, remember. I'm sorry, I'm talking backwards. It doesn't have a horizontal asymptote. It has a vertical asymptote at x equals plus or minus radical 2. So look at, oops. Look at the graph again. So radical 2 is like 1.7. So you can see kind of there's a vertical asymptote here and there's a vertical asymptote here. But watch what happens when x gets really, really, really small and when x gets really, really, really big. And I'm going to show you the y's too, because the y's are also going to get really small and really big. Now I haven't changed the function at all. My y equals is exactly still this equation. All I'm doing is looking what happens at the end of the function when x gets really, really big and y gets really, really small. It's hard to see it here, but it's actually a line that resembles the line y equals 3x. I'm going to squish it in so that you can see more. So I'm going to make my x min just be negative 1,000 as opposed to 10,000. Now you can see that it almost just looks like a line. Now this is the same function that in a 10 by 10 window looked like a little squiggle. But as you look farther and farther out, as you extend your window more, and you make it into negative 1,000 and 1,000 and negative 1,000 and 1,000, it starts to look just like y equals x, which is a straight line. So that's a good way to tell end behavior from a function by dividing the numerator by the denominator. Let's look at a cool one. That one was kind of boring because it was just a line. But what happens with like y equals 4x to the 5th over x cubed plus 2. Now again, there is a vertical asymptote because x cubed equals negative 2. Sorry. If I set the denominator equal to 0, so x cubed plus 2 equals 0, x cubed equals negative 2, x equals the cubed root of negative 2. And you can take the cubed root of a negative. So there is going to be vertical asymptote. But the end behavior is 4x to the 5th over x cubed, which means it's going to behave like a parabola. It's actually 4x squared, but the x squared part is all we really care about. We want to see how it behaves like a parabola, which means up, up. The right hand is going to go up and the left hand is going to go up as we get really, really big. That's what a limit is. I promise this is my last example and then I'll let you go. Hope you were good for the sub today. Again, it's hard to see. Let's look at it in a standard window. So it kind of looks like a cubic because the numerator is odd. But as we get bigger, it should look like a parabola, which means I really don't need the y. Let me just change the y. Because remember, if it looks like a parabola, it's going to go up, up. So I don't need any negative values of y. So let's change my y min to be 0. Still hard to see because I have too many x values. So let's change my x min to be from negative 50 to 50. See how the two ends go up? Just like a parabola, because the end behavior model is x squared. Alright, I'm going to stop talking. I hope that kind of makes sense. We're going to practice a whole bunch of this. We haven't really talked about domain and range in these, but we're going to tell domain and range from functions or from graphs, so I think you're going to be okay.